time we did section 2.5, but there's one thing I said I didn't get to, and that was z-scores. Right, so I'll cover that now. But before I do that, any questions about the rest of 2.5, or like the online homework if you've tried that? I haven't been good this semester yet at remembering to say, are there any questions on the homework before I get started into the lecture? So just know that you can always say, hey, wait, before you start, can you do this question or whatever. Sometimes I can even pull them up on the computer and go right into course compass. Now, I know it was the fourth one, and it counted it wrong. Whatever. Just ask questions. So yeah.
I had one question. I don't know if there's a problem on it or not, but I was going on my notes. How do you find that IQR again?
How do you find IQR?
Yeah.
Okay. IQR. Do you remember what IQR stands for? Interquartile range, and it is QG minus Q1. So it's just the difference. And the example that I used in class was the pulse data, and check me out for remembering this, but I think it's 78 minus 65, which was 13, was the IQR. Okay. So it's real simple to get if you have those quartiles, but you have to, do you remember how to get those quartiles? Why are you looking at that?
I thought that'd be, but I think it wasn't.
Oh, somebody else's watch or something? Okay, good. It looks like it's still going?
Mm-hmm.
Okay. So do you remember how to get the quartiles out of your computer? I mean your calculator, your TI-83? You do the one bar stats on whatever list you put your data in, and it will give you Q1 and Q3, and then it won't give you IQR, but you have to do the subtraction. Okay? All right, let's talk about z-scores. A z-score is a standardized score. Okay? So a z-score is a number that tells you the number of standard deviations that you are from the mean for a given individual. So I'll write that number of standard deviations from the mean. Okay? So before I write a formula or anything for that, in the pulse data, the mean was 72 and the standard deviation was 10, right? So what would the z-score be for somebody with a pulse of 82? Well, if it's number of standard deviations from the mean, how many standard deviations is that? 1. So the z-score would be a 1. Well, formally, the way that's computed, it doesn't have to be a nice multiple of standard deviations. It's just the value minus the mean divided by the standard deviation. So in terms of symbols, this is the individual value, x. So individual value minus the mean divided by the standard deviation. Okay? Now sometimes you'll see this written with x bar and sx, like I did. Sometimes you'll see it with mu and sigma. Well, that means they're doing population mean, standard deviation, instead of sample mean and standard deviation, but it's still called a z-score, it's still computed the same way. It's just the value minus the mean divided by the standard deviation. And what it lets you do is compare individuals from different distributions. Right? Now what I usually do at this point in class is I say, well, let's figure out who the tallest guy in class is. We know who that is, and he's ineligible for this, right? Because what are you, 6'9"? He's 6'9", and that's out there 3 standard deviations above the mean. He's a definite outlier. So let's get the next tallest guy. There's only like 2 of you, 3 of you in here. How tall are you?
6'1".
6'1". Any of you taller than 6'1"? Okay, so how many inches is 6'1"? 73? Does that sound right? So 73 inches. Right? So that's Eddie. Okay? Now let's get the tallest female in here. Amy, how tall are you? 5'9"? Anybody taller than 5'9"? How tall are you? 5'10". Anybody taller than that? 5'10". So how many inches is that? 70. Yeah, right on the back. And your name is? Morgan. That's right, Morgan. So Morgan is 70 inches tall. So who's taller? Eddie or Morgan? Duh. 73 minus 70, right? But who's taller relative to their distribution? Right? So in other words, who's more extreme, Morgan or Eddie? Well, if we go to the summary statistics on height, and you can't see them. If we go I'm going to have to hold it down because I need it that far down. For men, the standard deviation was 3.097. We'll call that 3.1, with a mean of 71.5. Somebody write these down. Maybe I should write them down here. So for men, it's 71.5, and the standard deviation was 3.1. For females, it's 64.8 for a mean, and a standard deviation of 3.2. So let's compute the z-score for each of them. Okay? So 73 minus 71.5 divided by 3.1. Do that one, and then we'll do Morgan. Now everybody should do these calculations. Don't just sit there and wait for my neighbor to do it, because sometimes you realize, well, I guess I'm not using my calculator right because I'm not getting the same number they're getting. And this one's a bit tricky. You really ought to use the parentheses around the top. The calculators are nice because they'll let you do a calculation all in one step, but you got to put parentheses around it or you get the wrong number. What is this one?
0.484.
0.484. Is that what everybody else is getting?
1.625.
And Morgan is 1.625. So let me ask the question again. Who's taller? Relative to their distribution, which one's further out in the tail? Morgan kicked your butt. Now, had we let Logan come in here, he would be, what, 81? 81 inches tall. Well, how much? 3.065. So Logan has a standard score, a z-score of 3.065. Interpret that number for me. What does that mean? He's just over 3 standard deviations above the mean. Is that rare? Yeah. That's extremely rare. Right? Remember how much percent is within 3 standard deviations? 99.7%. That's pert near 100%. So it's really rare. So there you go. That's why I excluded him, because I knew he'd still win. But it almost always works this way, where the male is taller, the tallest male in class is taller than the tallest female, but when we do z-scores, it almost always flips. Not every semester, but I did have one semester where I had one of the girl basketball players who was 6'6", which is really tall even for a girl basketball player. I mean, that's really tall. That's way more extreme than 6'9" for a guy. So she whooped up even before we did z-scores. But that's real rare. So I had to exclude her too. Okay, so that finishes up section 2.5. Any questions on z-scores? One of the things that you'll get used to doing as we go through some of the later sections is if they start talking about number of standard deviations, you got to remember, oh, that's a z-score. They're asking me for a z-score. They won't always say z-score. You just have to recognize it. If they're talking about number of standard deviations, that's a z-score. Okay, so chapter 3, we're ready to start today. And chapter 3 is about associations between two variables. So far, everything we've done, chapter 1 and chapter 2, has been talking about a single variable, one at a time. We talked about pulse, and then we talked about height, and then we talked about the other things. Now we're going to talk about two variables together. Is there an association between two categorical variables? We'll start with that. So association between two categorical variables. Well, what I'm showing here, let me dim the front so it's a little easier to see. Did that help at all? This is called a contingency table. Remember when we did frequency tables? When we had a categorical variable, a frequency table just says number of people that are in each of the categories. And then if we had a quantitative variable, we could divide into categories and say, well, number of people between 68 and 74, and do it that way, right? Well, that's what a contingency table is, only it crosses two variables into the same table. So a lot of times you'll hear these referred to as cross tabulations. So what are my two categorical variables in this table? Okay, smoking and exercising. So it's kind of hard to tell here, but this is the way the software I use prints it out. But smoking is this variable. So this is no, I don't smoke. Yes, I do smoke. Okay. So usually in the book or on an exam or whatever, I would have the word smoke written out here. So it's clear that that's my row variable, and exercise is my column variable. So a contingency table has rows and columns, just like a data file. Right? The variable whose categories make up the rows is called the row variable, and the one whose categories make up the columns is called the column variable. It's neat how we name things. All right? So here's the data. This is your data, 385 observations. So what I'm going to do is I'll raise this up. That makes those numbers a little bit hard to read, but I want to be able to write on there. I'm going to write a series of questions, and I want you to answer them from the data. What percent of people smoke? What percent of people smoke? I want you to use your calculator and figure that out based on this data. And this is non-smokers, smokers.
0.4.
Why are you shaking your head? You got it?
No.
Oh. They're going, you can't do that. You're breaking the rule.
Exercise, yes and no, up and down, smoke,
Right.
left and right.
So this is exercise, yes. Exercise, no. Smoke, no. Smoke, yes.
So 60.
Okay. Carolee, you got it?
I got 29%,
29%. Give me one decimal place on that.
29.1%.
29.1%. Okay, what two numbers did you divide to get that?
43 and 148.
Hmm.
So you did that?
Yeah.
Okay, that's not quite right. Let's see what she did compute. She looked at 148 as her denominator, so that's people who do what? Don't exercise. So she got the number of smokers among those who don't exercise. But I didn't say that here, I just said, of all of them, how many smoke, or what percent smoke. So what will the denominator be? The 385. This number sitting down here in the corner of the table is called the grand total. These two numbers here, 322 and 63, these are called row totals. Duh. Right? And these are called column totals. Okay? These are also known generically as the marginal totals of the table. And margin because the table itself are these four numbers. Those are known as the cells of the table. Right? So in the table are called the cells. And then the totals outside are called the marginal totals, and then the grand total. Notice that these two numbers, 148 and 237, add up to 385. These two numbers, 322 and 63, add up to 385. Right? So it's breaking down the same 385 people in two different ways. Breaking them into exercise, non-exercise, I pointed backwards, and non-smoke and smoke. Inside the table are the people broken out by combinations of those two variables. So this is known as a 2 by 2 table. Yeah.
So when you technically take the smokers, which is 63, divided by the 385?
So this is, that's not right. I got sidetracked and didn't come back and finish this. What you would do is say, well, I've got a total of 63 smokers. They answered yes to the smoke question. There's 63 of them. Divide by 385,
16.4.
and you get 16.4%. Okay? Now, that's really mathematically not precise because I wrote 63 over 385 is equal to 16.4. It's actually equal to 0.164, which then mentally you just move the decimal two places. I will not get picky about percentages versus proportions, but the online homework will. So if it says give the proportion and you put 16.4, it'll say, sorry, you're wrong. You also need to be very, very careful about number of decimal places. If it says give the percent to the nearest tenth of a percent, then you need one decimal place. If you give it 2, even though that's a better answer, it'll count wrong. So just be careful with that. Okay, so back to this 2 by 2 table. That means 2 rows, 2 columns. So this is R by C. And that's the way we always go in that order. It's rows by column. So if I ask you what are the dimensions of this table, then you count rows, then columns, and that's the dimensions of the table. Okay? Okay, that was the first question. What percent of people smoke? So what percent of people exercise? Aaron, you got it?
61.6%.
Okay, first tell me what two numbers you divide.
You said we were going to do exercise. I divided 237.
237, the column total for yes to exercise, divided by
385.
385. Very good. So 237 divided by 385. And you said that's what? 61.6%.
0.6.
Everybody getting that? All right, well that's too easy. Let's make it harder. What percent of people smoke and exercise? By the way, you'll have a test question or a series of test questions just like this. I'll give you a contingency table and I'll ask a bunch of questions about it. Okay? So, what percent of people smoke and exercise? So, let's see. 16.4?
Wouldn't it be the same as number one?
No.
Just yes and
Different
yes.
variable.
Where did this 63 come from? It came from this row total, right? So it includes people who don't exercise, 43 of them, and 20 who do exercise. Right? So that's a good thought, but not quite there. Do you have it, Caitlin?
5.2%.
5.2. And tell me what, I don't know if that's right or not, but tell me what two numbers, and I'll know if it's right.
I divided 20 by 385.
20 by, very good, that's it. So 20 by 385, and what'd you say it is, 5.2?
2. Yes.
5.2. Okay? Now, how did that, now we had to use a value inside the table from one of the cells. Inside the cells are people who meet two conditions at the same time. In this case, it's smoking and exercising. Notice that, and always think about the numbers that you're computing. Do they make sense? Does it make sense that only 5% of people would do that? Both smoke and exercise? Yeah, there aren't very many like that, right? I do a lot of cycling, and there's some guys that I ride with occasionally, and one of them smokes and just kills me. Like, we'll be out on this 40-mile bike ride, and we'll pull up to some place to get a drink of water or something. He'll light up a cigarette. You're just ruining everything you're out here doing. Well, at least I'm doing that. So, that's an and. Okay? Now, let's make it really fun. Let me get rid of this top line. And I'll say, what percent of smokers exercise? What percent of smokers exercise? Did we just compute that?
Not totally.
Not quite the same thing. This of smokers, what is that saying to do?
Divide by 6.
You don't use the grand total 385, you use only those who meet that condition. This is known as a conditional proportion, or a conditional percent. Right? So let me write that down. This is a conditional proportion. You condition on them being a smoker, then you compute the proportion who exercise. So what are the two numbers we're going to divide? 20 by 63. Which is, anybody have that as a decimal? 31.7%. Okay. So of those who smoke, 31% of them exercise. What percent of non-smokers exercise? I'm going to come down here to the bottom and do that one. I'm purposely saving this middle one. So here's another conditional one. What percent of non-smokers exercise? Those numbers are kind of hard to read here. But I just told you what numbers you're supposed to be using. So what two numbers do you divide?
217 and 322.
217 by 322. 217 over 322, and that gives you how much?
67.4.
67.4%. Okay? Now, what this whole section is all about is using numbers like that to make a conclusion. Is there an association, I erased it, but is there an association between smoking and exercising? What do we mean by association?
How do they relate?
Relationship, right? Is there a relationship? Okay. If there was no relationship, what would you expect to see?
No correlation.
Okay, but what would you expect to see in the numbers? It'd be more even, okay? These two numbers, the proportion of smokers who exercise compared to the proportion of non-smokers who exercise, you would expect them to be roughly the same. Now with real data, they're never going to be exactly the same, but you'd expect them to be close. Right? If it didn't matter whether or not you smoked as to whether you made the decision to go exercise, then you would expect that about the same proportion of smokers would exercise as non-smokers. So in order to look for association in a contingency table, you compute some conditional proportions and compare them. Right? So, is this number close to that number? No, they're way different. 31.7 compared to 67.4. Those are very different, so you'd say that's evidence of an association. Marginally, ignoring smoking, 61.6% of people exercise, right? So if there was no association, you would expect that both of these would be at about that level. They'd both be at about 61%. Now, how come, just out of curiosity, how come this number is so much closer to this one? You'd expect, wouldn't you, that when I pool them together, I'd get sort of the middle between 31 and 67? How come I don't? I get one that's a lot closer to 67 than to 31.
I think it's because there's more non-smokers and smokers.
Bingo, exactly. It's because there's 322 non-smokers and only 63 smokers. So most of the weight goes into that group when you pool them together. So it's going to be much closer to whatever their percent is than the smaller group. Okay? All right, well here's the same table with the conditional proportions filled in. So there's your, yeah, that's the same table. Is that the number we had? 31 points?
Well, we were kind of off at like this one.
Yeah, we did 31.8.
7. It's 7.4.
Oh, it's
9.
749. So if you round to one place, it goes to 7. But when you look at it at 2, it looks like it should round up to 3.8. But that's kind of tricky. So those are the two numbers you're comparing, right? Now, here's a very common mistake. And I will give you a question like this on the exam. I'll give you a contingency table and ask you compute some conditional proportions and decide if there's an association between the two variables. And people will do this. They'll compute this one, 67.39, using the row total 322. They'll compute this one, and they'll say, those two numbers are very different, therefore, yes, there's an association. Is that the right way to do it? No, in fact, let me make up a different table. Let me leave that first row the way it is, and then I'll erase these numbers and put in here 33.1% and 66.5%. I just made those up. These should add to what? 100. So that needs to be 66.9%, right? There is a table that would work this way, right? Not for our data, but there is. If you compare this number, 32.61 to 67.4, and say they're very different, therefore there is an association, you're making the wrong conclusion. Because it's these numbers you need to be comparing. If you compare these two, And I know what you're thinking. You're sitting there going, how do I know which direction I'm supposed to compare? Well, think about it. If you compare these two, if you use 322 as your denominator, right, so that's the thing you're conditioning on, then you just compared non-smokers to non-smokers. And of course, these two numbers are different. They have to add up to what? 100%. So if this one's 67, this one's got to be a bunch smaller. Right? So if you compare those two numbers, you're completely ignoring one whole row of the table. You haven't used all your data. So when you can use row totals or you can use column totals, but if you use column totals, then you compare different columns together. If you use row totals, you compare different rows. Don't use a row total and then compare different columns within that same row. That won't answer the question. Okay? So let's get some more practice. There's sex by exercise. Let me just go ahead and do that. First of all, these numbers that are in here, are they row variable, or I'm sorry, row proportions or column proportions? Which way was it computed? Did we condition on gender or did we condition on exercise?
Exercise.
Are you guessing? How do you know? Compute one, see what you get, right? To find out if this 57.69 is a row proportion or a column proportion, take 120 divided by 237, see if you get that number. Take 120 divided by 208, see if you get that number. Which one works? Divided by 208. So these are row proportions, which means we conditioned on which variable? Gender. We conditioned on sex. We said among the females, 120 out of 208 exercise. And that's 57.7% of them. Among the males, 66.1% of them exercise. Is that evidence of association? Or do I compare 42 to 57? No, don't want to do that. We used row conditioning, so you compare the two rows within the same column.
How close do they have to be to show?
I was hoping somebody would ask that question. And that's the $40 question. How close is close enough, right? And to be honest, this just the way the data fell this semester, that's kind of borderline. I'd say, well, there's a 9% difference between them. That's a fairly big difference, but it's not huge. It's not like the one we just saw for smoking. Later, as you get more of these kind of examples, you get better at it. But one of the things that, as a statistician, I look at is, well, what's my sample size? So 385, that's a pretty big sample. So a difference of 9%, that's a fairly big difference when you're looking at a lot of people. Had I been only looking at 30 people, then one person makes a 10% difference, right? So, 10%, 9% wouldn't be a big deal in that case. But when it's almost 400, then that's a fairly big difference. Now, the very last section that I will teach you this semester, section 11.2, we'll get a hypothesis test for contingency table. And it will let us compare and see, are those two statistically significantly different? Rather than, right now, what are we doing? We're doing what I call the eyeball test. We're just looking at the numbers, they're kind of close, but now on an exam, I would never have one that's in the gray area like this. I'd have one like the smoking one where, oh yeah, definitely, there's a huge difference. Or I'd have one where it was 67, 66, and you'd say, they're about the same. I won't have one in the gray area because I don't want to have to grade that. Because everybody have to have different explanations and all that. So this is what I would say, yeah, there's some evidence of association. It looks like males exercise at a slightly higher rate than females, but it may just be an artifact of the data. How about smoking and gender? Association or no association? Do
Yeah.
females and males smoke at different rates? Well, it's 19.7% of males smoke, 13.46% of females smoke. Is that enough different?
I think so.
It's kind of borderline again, but yeah, I'd probably say, well, it's a a fairly big difference, but again, partly because the sample size is so big. But it's kind of interesting, I have the benefit of seeing semester after semester after semester of data, so I can know that this trend usually holds, that they're close, but males are slightly higher. Same thing with exercise. They're always close, but males are slightly higher. They actually were further apart this time than usual for the exercise. 9% difference. It's usually more 4 or 5% difference. And for smoking, it's usually about like this, 5 to 6% difference between them. So once you see something repeat over and over, then that's more evidence that, yeah, there is an association. Okay, this is health rating by smoking status. So top row is non-smokers, bottom row is smokers. Notice that you have the same row totals that we had before, because I have the same row variable. 322 and 63, same grand total. But now my column totals are all different because I have a different categorical variable there. Okay. Now, before we start messing with the numbers here, there's a couple of more terms we need to get. And that's response variable and explanatory variable. The response variable is the variable that you're sort of interested in, the one you're measuring. So it's like, what percent of smokers do something, like exercise? Well, exercising is the percent I'm interested in, right? The definition in the book says the response variable is the outcome variable on which comparisons are made. So, variable on which comparisons are made. So when we were asking about exercise and smoking, which one was the response variable? Exercise. Because it was the percent who exercised that I compared. Percent of exercise in one group compared to the percent of exercise in another group. So the explanatory variable is the variable that divides into the groups to be compared. Let's say groups to be compared. In the book he says, defines the groups to be compared with respect to values on the response variable. So we compared smokers and non-smokers with respect to their exercise stats. So we used explanatory variable as smoking, response variable as exercise. Okay? Now, one way to kind of figure that out, you'll have some homework problems where they say, which of these is the explanatory variable and which of these is the response variable? And they'll give you some scenarios, right? One way that I always kind of figured out is, well, which one could, it's not guaranteed that it does, but could conceivably cause an effect on the other variable. And sometimes that's clear cut, sometimes it's not. For instance, health rating and smoking. Which one of those makes more sense to be the cause of the effect, and which one is the response to the effect? Smoking is the cause, and health is the effect. Right? That makes more sense. It doesn't make sense for people to say, wow, I'm in poor health. I guess I might as well be smoking. Right? Or maybe I'm in poor health, I should quit smoking. But knowing what your health is doesn't cause you to make a decision of whether or not to smoke, except in the extreme case where you get, cancer or something and you have to quit smoking. But the other way makes sense. Somebody chose to be a smoker, and they tend to rate their health lower or whatever. They have a response to that. Yeah.
So the cause would be the explanatory and the response would be the effect?
Exactly.
Okay.
Yeah. So the cause is the explanatory variable, and the effect is the response variable. Okay? Now, before I hit the next page, I want you to compute. Let's do, let me see how long this looks if I, yeah, you can see. Get this stuff off of here. I want you to compute some conditional proportions. It says at the top to compute all of them, but we won't take the time to do it all. Let's compute the conditional proportion of 2s and 4s conditioning upon smoking. And sometimes that's the way they say it. Rather than say, of those who smoke, they'll say something like, condition upon the smoking status, compute the proportion who were a 2. That's another way of saying the smoking status is my denominator. So compute those. I want a number in here, in here, in here, and in here. So 4 numbers to compute. And then once we have those numbers, I'll fill in the rest of the table, and then we can talk about whether or not it's evidence of an association. And I'm going to walk around and look at what you write. And then if you have no idea even how to get started as I come by, just ask the question.
And what are you asking again?
Okay, that's a good question. I'll write it another way. I want these things. Conditional upon smoking. Let me just add AL. So it's conditional. That's how it's usually worded in a sentence. Conditional upon smoking, compute the proportion of 2s. And then do it again for 4s. Okay? Now another way to say that is, of those who smoke, what proportion say they're a 2? And then of those who don't smoke, what proportion say they're 2? That says the same thing as this math speak. Okay, and what numbers did you divide to do this? Because I don't know the numbers of them.
13 divided by 21. Divided by 21.
Good. Well, write down just the fractions. You don't have to. I don't know if you're doing it right. I'm sorry, I told you you were okay.
Oh, no.
You did math. Which way did you go? That is correct.
Oh, it is.
Okay. And you heard me tell her.
Yeah.
Yeah, you're doing the same thing. Okay, the trick here is to figure out what is the denominator. What should you be using as the bottom of your fraction? That's good. Which one? You were wrong. You're going wrong. Now you're fixing it. Which one did you? Yeah, these look right. I remember those numbers. Which did you go this way and this way?
Yeah, this is.
Yeah, that's right. Okay.
So, should the denominators be 2186 or is that wrong?
That is wrong.
Okay.
Now, her question, about half of the class is doing 13 over 21 and 169 over 186, and that's the wrong direction, right? The thing you condition upon, you want those totals.
So 3.
That's your denominator. So we're conditioning upon smoking, so I want the smoking totals to be my denominator. So I want 13 out of 322. So I'm going to write that in the box here, or in the circle, 13 out of 322. And then this one would be 169 out of 322. And then 8 out of 63. And 17 out of 63. Everybody understand that? And for a while, you'll struggle with, well, which total am I supposed to be using here? But get used to it. It's always worded in a certain way. And a lot of times they'll use the of clause. Of those who smoke. And that makes it easier, I think. Writing it this way, it gets pretty confusing. So, but it says condition upon smoking. That means use the smoking totals as the denominator and then compute the proportion 2s and 4s. Okay? So, let me pull that down and then I'll hit the page down button and fill in the numbers. Is this what you got? 4.04, 12.70, 52.48, 26.98. Okay? And then the rest of them I've already computed and they're filled in there as well. Do you see evidence of association between whether or not somebody smokes and how they rate their health? Okay? I agree. Very strong association. Very clear. What is it that's tipping you off?
Half of the smokers are on 3 and half the non-smokers are on 4.
Yeah, these 4 cells right here kind of tell the whole story. This one, 27 to 57, right? And then it completely reverses right there. If there was no association, what would you expect?
They'd all be even. All.
Every column, the columns wouldn't be the same, right? But within a column, you'd expect these 2 numbers to be about the same, these 2 numbers to be about the same, about the same, about the same, and about the same. And they should occur in about the same proportion, same ratio that these column totals fall. Question?
So like would an example of them trying to be like the same would be like smokers and non-smokers whose those numbers were their favorite number instead of their health rating? Like
Yeah.
would it be the same?
Yeah. You know,
Okay.
pick your favorite number out of these 5 numbers, and you think, well, it's just kind of random.
They'll be random.
Smoking shouldn't have anything to do with it, so you expect them to fall in about the same percentages.
Okay.
Or number of children you've had, right? Smokers tend to have children at about the same rate as non-smokers, as far as I know, right? So if there's no relationship, you'd expect to see that they all answered about the same way. Okay? Okay, now, this is a graph known as a side-by-side bar graph. And I showed you, and I'll bring it back up in a second, a different looking side-by-side bar graph for this same data already when we did the chapter 2 stuff. But I kind of like this one because it puts the bars that you should be comparing right next to each other. Right? So this is people who answered a 1, right? The proportion among smokers who answered a 1, the proportion among non-smokers. Well, there aren't any non-smokers. Remember, there was a 0 in that cell. Right? And you have to look at the legend to see which is which. The non-smokers are the lighter colored blue, and the smokers are the dark ones, just like their lungs. So, you see that complete reversal that we pointed at in the numbers. You see 27% versus 50-some, and then they reverse. That's very strong evidence of association. Okay? That's all the time we've got. So, have a great weekend. I think it's supposed to be stormy tonight, and then